Okay, now from the previous section, we worked out the F resultant here and we found it to be 2,800 newtons. Remember that work done, okay, the net work done equals to F, which is the resultant force, times the displacement moved. So this would be equal to 2,800 times 150, and that would be, okay, so this is 2,800 times 150, and the answer is 4.2 by 10 to the power minus 1, 2, 3, 4, 5 joules of energy. So that will be the net work done here. Remember, here I showed you how to find the resultant force when you're given friction and applied force. And you could use a different approach to do this question here, like we used the work net equals delta EK. You can do the same here. Now moving on. In the same question, is mechanical energy conserved in this situation? The answer is no. It is not conserved. Why? Because there's an external force, there is friction here, okay? There is, or you may say that the system is not closed, or the system is not isolated, not closed, okay? Because there is friction. We've got friction here. So this is not a closed system. Okay, now quickly, let's have a look at this question here. It says a rescue helicopter is stationary and it hovers above a soldier. The soldier of mass 80 kilograms is lifted vertically upwards through a height of 20 meters by a cable at a constant speed of 4 meters per second. The tension in the cable is 960 newtons. Assume that there is no sideways motion during the lifting. Air friction is not to be ignored. Now that's very important. We used to air friction, ignore air friction. This time, air friction is not to be ignored. Okay, this diagram here shows what is happening or summarizes that question there. There is the soldier lifted up and the tension in the cable and your helicopter there. State the work energy theorem. 1. The net work done on an object is equal to the change in its state or in its kinetic energy. Okay, so that is what the work energy theorem is saying. 2, we are asked here to draw a force diagram showing all forces acting on the soldier whilst lifted up. Okay, now you can use a dot to represent your soldier. Okay, then on that dot we know of the force that is pulling the soldier upwards, and that is the tension in that rope. And this tension is also given to us, we are told, is 960 newtons. On the other hand, we know there is the force of gravity on the soldier. Okay, let's see where I think we are given the mass of the soldier. It's 80 kilograms. So Fg equals mg equals 80 times 9.8. So we can even get, you don't have to be calculating. I'm doing this because I'm teaching you, so you can get all these things here. So that's 80 times 9.8, and the answer is 784 newtons. So we have, that is the force of gravity Fg. Okay, apart from Fg, we also have what? the force, the frictional force due to the air molecules. Okay, so this is frictional force. Okay, we don't know what it is. Maybe we will have to work out at some point in this question here. But this force diagram here has shown all the forces acting on the soldier. Okay, and because we couldn't ignore air friction, that is also represented as well. So you'll have two forces pointing downwards. Okay. Now, write down the name of the non-contact force acting on the soldier. What's a non-contact force? These are forces that exist due to fields, things like gravitational fields, electrostatic fields. Okay, there we have got non-contact forces. We don't have a rope attached to something to pulling, and we don't have to see physically something pushing on something else. No. So the force is non-contact, but it is there due to the field. Now, which one is that? It is definitely your gravitational force. So the question says, write down. It is the gravitational force, which we said FG in our drawing there. That brings us to the end of this lesson. Hope you enjoyed it. And it's from me, Tinyiko TK. It's bye-bye.